So this is a lesson for 4-1. What we're really focusing in on today is on picture patterns, all right? The learning target, I can describe a sequence in words, write it numerically, and draw or write what the next terms in the sequence look like. First of all, we have some vocabulary words, all right? A sequence. A sequence is a pattern involving an ordered arrangement of numbers, figures, letters, or other objects. The term in the sequence is an individual number, figure, or letter in the sequence. All right. So, like, this would be the first picture or first term in the sequence. This would be the second one, the third one, the fourth one. Examples of sequences are shown, describe the pattern, draw or describe the next terms, and represent each sequence numerically. So we're going to look at probably about like 12 or so of these. All right. Every one is slightly different. All right. But what we're really looking for is what is happening in the pictures. Are we adding a certain number each time or subtracting a number of something each time and things like that? So looking at this one called positive thinking, it says analyze the number of dots and describe the pattern. So just to save us some time, this picture has 25 of the little dots. This picture has 21. This picture has 17. This picture has 13. If you take a look at the pictures each time, what exactly is happening in the pictures? Well, to get from 25 to 21, we're subtracting by 4. To get from 21 to 17, we're subtracting by 4. To get from 17 to 13, we're subtracting by 4. So our next three numbers in the sequence, they would have 13 minus 4 is 9, and then we would have 5, and then we would have 1. So those would be the next three numbers in the sequence. You're also going to have to draw the pictures in Class Kick today. So when we take a look at these, notice that this one has 6 dots. I'm going to call it like an arm or a leg, like maybe think of like an octopus type thing. So this has 6 dots going out. This has 5 dots in each direction. This has 4 dots in each direction. This has 3 dots in each direction. So one dot is disappearing from each of the ends each time. That's what I would write in the description. All right. That we're losing 1 dot each time. So drawing the next 3 in the pattern, all right, we ended up with 3 dots in each direction. So now we're going to have our 1 dot in the middle. But now on this next one, we're going to have 2 dots in each direction. And then in the next one, we would have our dot in the middle and then have 1 dot in each direction. And then we would just have our 1 dot in the middle. So that one's pretty straightforward, pretty easy. You have to know the difference between finite and infinite, right? You would think that this would be pronounced finite, but it's not, it's finite. So we have finite and infinite. Finite and infinite are opposites of each other. Infinite, let's look at first. Infinite, notice in our number pattern, right? It's getting bigger and bigger and bigger. It's just going to keep on growing and growing and growing. In infinite pattern, the pattern will go on forever. The pattern will never end, right? It will just keep on going and getting larger and larger and larger. Eventually, you'll end up with numbers that are in the millions and billions and trillions. So the pattern will never end. There's no end to it. But a finite pattern, notice that we're getting rid of the bottom row of blocks each time. So we're getting rid of 4 blocks here. We're getting rid of the 3, the 2, 1. Eventually, we ran out of blocks. So the pattern ends. The pattern stops. The pattern terminates due to some sort of limitation. In this case, we were running out of blocks, so we couldn't take away any more because the blocks, we ran out of it, all right? Where this one just gets bigger and bigger and bigger. This one eventually goes down and stops for some reason. So let's take a look at a couple more of these, all right? So these are the ones that we're looking at. We're not going to fill out that table. So family tree. Jessica is investigating her family tree by researching each generation or set of parents. She learns all she can about the first 4 generations, which include her 2 parents, her parents' parents, her parents' parents' parents, and her parents' 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 parents. So let's draw what this would look like. So she learns all about her 2 parents. So she has her mother and she has her father. So at the first generation, we're starting off with 2. Now, her mother each had 2 parents, a mother and a father. Her father had a mother and a father as well. So now that we're doing her parents' parents, we would have 4 in our pattern. Well, each of those parents had parents as well. So mother, father, mother, father, mother, father, mother, father. So now we're looking at 1, 2, 3, 4, 5, 6, 7, 8. So now we took care of her parents, parents, parents. The next one are each of those parents had 2 parents as well. Mother, father, 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 mother, father. So now there are 16. So our pattern would be increasing. It would keep on going 2, 4, 6, 8. It's doubling each time. So we're starting at 2 and doubling each time. This would be infinite. All right, this would be infinite because our pattern would keep on getting bigger and bigger and bigger and bigger and bigger as our numbers go. It is increasing. All right, so we're starting off with 2 and we are doubling each time. So we're multiplying by 2 each time. That's what would be happening there. Let's take a look at the next one. A collection of squares. Now, when you take a look at this collection of squares, just to save us some time, this one has 49, this one has 36, this one has 25, this one has 16. So what is happening each time? Well, we're losing squares each time, right? We are losing the top row and the side row each time, right? As we go from picture to picture to picture, it's getting smaller and smaller and smaller. So this would definitely be finite, all right? This would definitely be finite. Our next number in the pattern, all right? Now notice that these are really perfect squares, all right? This square is 7 by 7. This one is 6 by 6. This one is 5 by 5. This one is 4 by 4. So if we had to draw the next numbers in the pattern, all right, we would have a 3 by 3 as our next picture in the pattern, which would have 9. Then our next one would be, after we lose a row and lose a row on the side and on the top, it would be 4 by 4. Lose a row, we would just have 1. And then we would have to stop because we wouldn't have any left. So our pattern is we're losing the side and top row. These are really perfect squares. We're starting off at 7 by 7, losing a row each time. Or you could say this is really 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, 6 squared, 7 squared. But we are definitely decreasing each time because the numbers are going down and they're perfect squares each time. Take a look at the next one. Al's omelets. Al's house of eggs and Nat makes omelets, whatever. Al begins each day with 150 eggs to make his famous Best Western omelet. So he starts each day with 150. After making 1 omelet, he has 144 eggs left. So we go from 150 to 144. After making another omelet, he has 138 left. After making another omelet, he has 132 left. So what are we doing each time? Well, to get from 150 to 144, we are subtracting by 6. To get from 144 to 138, we are subtracting by 6. 138 to 132, we are subtracting by 6. So our pattern is that we're starting at 150 and subtracting by 6 each time. Well, would this be finite or would it be infinite? This would be finite because eventually we would run out of eggs. All right, eventually we would get to 0 and we would run out. The pattern is decreasing. All right, the pattern is decreasing because we're subtracting by 6 each time. If we were to continue on with this pattern, we would have to subtract 6 again. So then we would be at 126. We would subtract 6 again. So our next number would be 120. And then our next number would be 114. You will have to continue the patterns here, or just say what they look like sometimes. Depends on how the question is being asked. Take a look at Mario's mosaic. Mario is creating a square mosaic in the school courtyard as part of his new art project. He begins the mosaic with a single square tile. Then he adds to the single square tile, he creates a second square made up of 4 tiles. Then he adds his third square is made up of 9 tiles. His fourth square is made out of 16 tiles. So what are we doing each time? We have, first of all, we are increasing. Now this one, to determine whether it's finite or infinite, let's just say that he has access to an unlimited number of tiles. Now, yes, you maybe run out of money or something like that. But let's just say that if we just kept on with this number pattern, let's just say for lack of an argument that it's going to be infinite because it keeps on getting bigger and bigger and bigger. Let's just say that he had unlimited resources. So it would keep on getting bigger and bigger and bigger and bigger. Notice what we're doing each time. We're starting at 1, but then we're counting by consecutive perfect squares, because 1 squared is really 1 times 1. 2 squared is 2 times 2, which is 4. 3 squared is 3 times 3, which is 9. 4 squared is 4 times 4, which is 16. So that would be infinite. The troop of triangles. So take a look at this pattern. You can clearly see that we are adding a row each time to the bottom. So we have 1 triangle here, 3 triangles here, 6 here, 10 here. What are we doing each time? Well, we added by 2, we added by 3, we added by 4, because we're adding 1 to the bottom row each time and moving all the other ones up. So that's what our pattern would look like: 1, 3, 6, and 10. Obviously, the next one, if we had to do the next one would be a +5. So it would be 15. The next one would be a +6. So it would be 21, and so on and so forth. So this would be infinite because we could keep on going and keep on going and keep on going. I can spell infinite. It is increasing. And again, we are starting and with 1 and then adding each time to the bottom row. Adding 1 each time to the bottom row. Gamer Guru. Micah is trying to beat his high score on his favorite video game. He unlocks some special mini games where he earns points for each one he completes. Before he begins playing the mini games, 0 games completed, Micah has 500 points. After completing 1 mini game, he has a total of 550. After completing 2 mini games, he has a total of 600. And completing 3 mini games, he has a total of 650. Write down what you think this pattern looks like. Write down what you think this pattern looks like. And also, I want you to say, is it increasing or decreasing? Is it finite or is it infinite? So what does this pattern look like? Well, he's starting off with 500 points. He plays a mini game and now he has 550. He plays another mini game and now he has 600. He plays another mini game and now he has 650. So that's what our pattern looks like. We are clearly adding 50 each time. All right, we're clearly adding 50 each time. This was starting at 500. This is clearly increasing. And let's just say it is infinite. Yes, maybe he would run out of time to keep on playing, but let's say that this was his only life that he had and he could play all the time. So our pattern, our numbers would keep on going up. So let's just, for lack of a better argument, say that it is infinite. Let's take a look at the next one, Polygon Party. So we have a triangle, a square, a pentagon, and a hexagon. Write down what you think the pattern is, whether it is increasing or decreasing, what's happening each time, and whether it's finite or whether it's infinite. So what we're counting on is sides. The triangle has 3, the square has 4, the pentagon has 5, the hexagon has 6. So starting with 3 sides, we are adding by 1 side each time. So we are definitely increasing. And this would be infinite. All right, we could keep on drawing shapes that have 100 sides to them. All right, so we could keep on going and going and going and increasing the number of sides. So the pizza contest. Jacob is participating in a pizza making contest. Each contestant not only has to bake a delicious pizza, but they also have to make the largest pizza they can. Jacob's pizza has a 6-foot diameter. That is a huge pizza. After the contest, he plans to cut the pizza so that he can pass out slices to share. He begins with 1 whole pizza. Then he cuts it in half. After that, he cuts each of those slices in half, then cuts each of those slices in half, and so on and so forth. So he's starting with his 1 slice of pizza. He's then taking that and cutting it in half. So now he has 2 slices of pizza. He's then taking those 2 and cutting it in half again. Cut it in half, cut it in half. So now he has 4 pieces of pizza. Then, so he begins with 1, we did that, cuts that in half, we did that, cuts that in half, did that, and now this last one says he's cutting it in half 1 more time. So now he has 8 slices. Well, what are we doing each time? We are multiplying by 2 each time, because we're taking each of those and cutting it in half. So we're multiplying by 2 the total number of slices of pizza. Now, technically, this is increasing because we're increasing the number of slices of pizza. Yes, each slice is getting smaller, but we're talking about the number of slices of pizza. And would it be infinite or finite? Technically, it would be infinite. Yes, you're going to end up with microscopic pieces of pizza, all right? But technically, let's just say for lack of a better argument, this would be infinite, all right? Because technically we can keep on going smaller and smaller and smaller and smaller. All right, try this one on your own. Write down what the pattern would be. Miranda's uncle collects rare coins. He recently purchased an especially rare coin for $5. He claims that the value of the coin will triple each year. So even though the coin is currently worth $5, it would be worth $15 next year. In 2 years, it would be worth $45, and in 3 years, it would be worth $135. Go ahead and write down what the pattern would be, please. Don't make this harder than what it is. All right. This first year, it is worth $5. The next year, it's worth $15. The next year, it's worth $45. And in 3 years, it's worth $135. So that's what the pattern would look like here. What are we doing each time? Well, it has the word triple. Triple means that we are multiplying by 3 each time. So we are definitely increasing. We're starting at 5, multiplying by 3 each year. Technically, this would be infinite again, all right? Now, is the coin going to keep on getting worth billions and billions and billions of dollars? According to this scenario, yes. Realistically, probably not, but it would be worth an infinite amount eventually, all right? Don't make this harder than what it is. You have to make sure that you read the directions and do what's being asked.